Hi, and welcome to the problem session for Lecture 13. This is the first one beginning the last part of the course on multivariate calculus. And here we're just going to go through some, we're going to go through some examples of partial derivatives and multivariable integrals. We're going to start with talking about a problem. This one is from the book, just because it gives you a nice example of how this stuff is used substantively. Okay, so let's start there. Here's the model of three variables that looks like this. Okay, this is a general multiple regression model of the kind you will see very, very often in your studies. You're reading and you want to know what the partial derivatives are. Well, let's see. Partial f partial x equals beta 1, and partial f partial w equals beta 2, and partial f partial z equals beta 3. Now each of these correspond to the marginal effects of x, w, and z respectively, holding all other variables constant. And we talked about this before when we first introduced these things. Understanding partial derivatives is very important because it's central to the proper interpretation of your multiple regressions. In this case, it gives you the sort of theoretical warrant for saying things like, I'm holding other stuff that I'm holding all the stuff that I'm regressing constant, right? So I'm looking at the marginal effect of x on y, holding w and z constant, right? This gives you that justification for doing that. Okay. And it just comes from the partial derivatives because when you take a partial derivative, you're treating everything else as a constant. So when I take the partial derivative of f with respect to x, I am just ignoring w and z completely. Okay, I'm treating them as constants rather. Okay, now we can do an interaction term, which is the reason I'm doing this example here. Write it again, beta 0 plus beta 1x plus beta 2w plus beta 3z. No, you always have to include the constituent terms in an interaction equation. And then have an interaction term here. Same deal. What are the derivatives? I'm sad I don't have cut and paste capabilities here. So this is beta 1 plus beta 4w, because when I'm taking the partial derivative with respect to x, there's this term over here, and also this term. I treat w as a constant, so the constant is beta 4 times w, which is how I get this thing down here. And then the same thing with different one. Partial f partial w will be beta 2 plus beta 4x for the exact same reasons. And since the interaction term for z does not involve z at all, we just keep beta 3 there. Okay. Now what does this mean? Well, this means that the marginal effect of each of x and w on y depends on the other variable, right? So the marginal effect of x on y depends on the value of w at a given point. And the same thing for w, the marginal effect of w on y depends on the value of x at a given point. That's important because that tells you that the marginal effects are actually changing, right? They're actually variables themselves. So when you work out how to interpret this, you're going to end up writing these kind of marginal effect plots where you can look at this thing at 0, right? So for instance, let's look at this marginal effect over here. Let's plot the marginal effect of f on x, y on x. No, this is the thing you care about, right? You actually care about the marginal effect of x on y, not just beta 1. You don't care about the coefficient itself. What you care about substantively is how changing x changes y. That includes the interaction term over here. So the total effect of x and y is this entire boxed expression right here. So we can graph this thing. At w equal to 0, we have say beta 1. But as we change w, then we change the marginal effect of x on y. If beta 4 are positive, we might get, for instance, this. Right? And if we do some error bars around this thing, right, we might end up something like this. What that tells you is at low values of w, we have a non-significant effect of of x, right? So whereas at higher values of w, the value of the effect of x on y is increasing. right? It is positive and significant here, right? So we can talk in more detail about this, and I'm just being very, very rough here because this is a bigger topic. But you can do other things with this. You could say, if beta 1 were negative, but you had some really great data, right? You might say that it starts off negative, it's insignificant, and then goes up this way as W increases. And that not only, should be dotted, that not only tells you that the marginal effect of x on y is changing, but actually flips sign. When W is low, the marginal effect of x on y is negative, but when it's high, it's positive. And that's a really important substantive meaning. So it's really important to understand properly how to deal with these interaction terms. Okay, so that's that. Okay, now we'll go a couple more concrete examples that are new on how to take partial derivatives. We'll do a couple of these. Actually, I think we just do one of them. I apologize. We just do one of them. There are a couple in the problem set. A couple of new ones in the problem set. X, y, z minus x to the third z e to the y x. How do we do this? Well, we have three partials. The first term, we're going to ignore the y and z. We're going to treat them as constants. So now we have just 3yz times the derivative of x is 1. The second term, we have x in two places, so we use the product rule. There's a z out front of the whole thing, so that's a constant. The product rule says you take the derivative of the first, which is 3x squared, times the second, plus the derivative of the second, plus the first, times the derivative of the second. The derivative of e to the yx, y is a constant, so you just pull it down, and you get e to the yx. If that wasn't clear, you're actually technically using the chain rule here for taking the derivative. You make u equal to yx, and you'll see the whole thing works out just fine. So u equals yx over here. And that gives you the derivative there, and I'm not going to simplify because why bother. For y, again, you have 3xe, those are constants, times derivative of y, which is 1. There's only y in one place here. Both x and z are constants, so we leave them out front. The derivative of e to the yx, you pull down the x because that's a constant. So actually you get x to the fourth here. And you get back e to the x again, e to the yx again. And then finally, partial f, partial z is going to be y and x are both constants. Derivative of z is 1. And then there's only one z in one place, and it's just a z. So even though this is complicated, x cubed e to the yx is just a constant. And the derivative of z is again 1. And that's it. We're done. Those are partial derivatives for this function. Again, partial derivatives are not any more difficult than total derivatives. You just treat every variable that's not the one you care about as a constant. Okay, so now we're going to do one example of a multivariate integral. Now this one looks messy on first glance, right? There's an e to the x to the fourth up there, and there's no x out in front of that thing, so that looks really messy. Maybe we can't do it at all. But let's just try it out, because, we made this up to work. So, now we have to do the y integral first, because there's an x in the bound of that one. So we're going to do this one first. And have to figure this out. So we're going to move so this is going to equal, we can move the x stuff out. And just do the integral from 0 to 1 of y squared dy. What's that? Well, the integral from 0 to 1 of y squared dy, we use the power rule. We get 1/3 y cubed, and we're going to evaluate that from 0 to 1. Now remember, the power rule is you take the, you raise the exponent by 1, and then divide by the new exponent. Y to the y cubed evaluated at 0 is 0, so this is just 1/3. Oh, I'm being silly. This is an x. That's the whole point of this. That's an x bound. This is also an x bound. So it's 1/3 x cubed. The 0 part's still true, but there's an x bound at the top. So the top bound is x. So you have 1/3 y cubed evaluated at x. That's just 1/3 x cubed. Now, we can plug that back in here, and the big integral is 0 to 1 e to the x to the fourth times 1/3 x cubed dx. Now note you have an x cubed at front, so you actually can use substitution. So let's set up u equal to x to the fourth. That implies du equals du dx, which equals 3x cubed dx. So dx equals 1 over 3x cubed du. So we change variables. We end up with 0 to 1, 1/3 from here, 1/3 from this thing that exists already, and 1/3 from the change of variables gives us 1/9 out front. E to the u, the x cubed divided cancels with the 1 over x cubed, so we're left with only du. Now we don't have to change bounds at all even, because x to the fourth evaluated at 1 is 1. X to the fourth evaluated at 0 is still 0, so the bounds stay the same actually. So the integral is just 1/9 e to the u evaluated from 0 to 1. We keep the same bounds, and that's 1/9 e minus 1. And that's it. We have solved the multivariate integral. Again, multivariate integrals aren't so bad. They're not much different than single variate integrals. You just have to do one at a time, making sure only to take care of the ones that involve bounds that have other variables in them first. If you do that, you'll be fine just taking it one at a time and doing the ones with the other variables in them in the bounds first. Here, there's an x in the y integral, so we have to do the y integral first. That's it. That finishes lecture 13. Thank you very much.